we are going to write the correct form of wave function. Already we have written as psi is equal to a sin kx plus b cos kx, and applying the first boundary condition, we have b is equal to 0, so that psi is equal to a sin kx. In the second boundary condition, we have a relation that kl is equal to n pi, and from here k is equal to n pi by l. This can be substituted here, so that psi is equal to a sin n pi x by l, equation number 1. Now, the normalization condition, I have already explained about normalization condition. Integral psi of rt, psi star of rt, d tau is equal to 1 for a particle. We are considering a particle, so that we can use this normalization condition. Integral psi of rt, psi star of rt, d tau is equal to 1. Or simply integral psi of rt, instead of psi of rt, we can write simply psi. Psi star of rt means simply the psi. So, integral psi star, instead of dx, d tau, I am writing dx because we are considering the x direction, x equal to 0 to x equal to l. So, x values are varying, so that we can take dx. Okay. So, integral psi star dx is equal to 1. And the boundary conditions are 0 to L. These are the limits, x equal to 0 to x equal to L. So, the limits are 0 to L. Integral 0 to L psi star dx is equal to 1. Now we are changing the normalization condition according to our situation. Integral 0 to L psi star dx is equal to 1. But we know the relation psi star is equal to mod psi square. So that integral 0 to L mod psi square dx equal to 1. Okay. Now we have psi is equal to a sin n pi x by L. Now we have to find modulus of psi square. Since it is a positive quantity, modulus can be neglected. Now we have to find only the square of this size wave function. So what is the square? Integral 0 to L a square sin n pi x by L square, which means sin square n pi x by L. Okay. So, a square sin square n pi x by L dx is equal to 1. And that will be our integration. Now, a square can be taken outside. A square is a constant. Integral 0 to L sin square n pi x by L dx equal to 1. Now, we are applying a trigonometric relation. Sin square theta is equal to 1 minus cos 2 theta by 2. Expansion for sin square theta, 1 minus cos 2 theta by 2. Instead of theta, we have n pi x by L here. So, format of sin square theta, right? So, expand this a square integral 0 to L 1 minus cos 2 theta. Cos 2 theta, what is theta? N pi x by L whole divided by 2. 1 minus cos 2 theta by 2 dx is equal to 1. 2 is a constant, that is a square by 2 integral 0 to L 1 minus cos 2 n pi x by L dx equal to 1. That is a square by 2 integral 0 to L 1 into dx 1 dx minus cos 2 n pi x by L into dx, second term cos 2 n pi x by L dx is equal to 1. So, a square by 2 integral 0 to L 1 dx minus integral 0 to L cos 2 n pi x by L dx is equal to 1. Split the two integration. Integral 0 to L 1 dx is our first integration. Integral 0 to L, this will be our second integration. But the value of the second integral will be 0. So that we can neglect this factor. So, we have a square by 2, only the first integral 0 to L, integral 0 to L dx is equal to 1, since the second integral vanishes. That is a square by 2. What is integral dx? X within the limit 0 to L. Integral dx is equal to x. We have to apply the first, in the limits of this integration 0 to L equal to 1. A square by 2, upper limit minus lower limit. L minus 0 is equal to 1. That is a square by 2. L is equal to 0. L is equal to 1. And a square is equal to 2 by L, or a is equal to root of 2 by L. So, what is our amplitude? It is nothing but root of 2 by L. So, that our wave function psi is equal to a sin n pi x by L was the format of wave function, equation number 1. So, psi is equal to, instead of a, we can now substitute root of 2 by L. Root of 2 by L sin n pi x by L, n equal to 0, 1, 2, 3, etc. So, in general, we can write psi n is equal to root of 2 by L sin n pi x by L. This is known as Eigen wave function. So, we can find psi 1, psi 2, psi 3, etc. by substituting n is equal to 1, 2, 3, etc. So, that psi 1 is equal to this value value, psi 2 is equal to this value, and psi 3 is equal to this value. These are different eigen wave functions.